Hello everyone. In this video, I'll discuss about electric dipole and its applications. This is a part of electric charges and fields chapter. So first we'll define what is electric dipole. Electric dipole, if suppose we are having two charges of equal magnitude, one is positive charge and the other one is negative charge, they are separated by a fixed distance, both are having same magnitude of charge, but they are separated by a fixed distance. The distance, if I assume that as 2L, then this system will call that as a electric dipole. So electric dipole consists of two charges of equal magnitude but of opposite sign, separated by a fixed distance. Separated by a fixed distance, we'll call that as dipole. For this dipole, we'll define a parameter called dipole moment. Dipole moment will represent with the letter P. So it is product of magnitude of any one of the charge into distance between the two charges. We have to just take magnitude of the charges, and it is a vector quantity. It is always directed from negative charge to positive charge, and its units are coulomb meter. So its corresponding dimensional formula will be, for coulomb it is ampere into time, and for meter it is length, so that it is its corresponding dimensional formula. And this dipole moment or electric dipole moment, it obeys vector law of addition. Obeys vector law of addition. That means if suppose two dipoles are inclined at an angle theta, this is dipole 1 of dipole moment P1 and this is dipole moment P2, and they are inclined at an angle theta, then their resultant dipole moment P net we can take like this. This will be sum of individual dipole moments. Their magnitude will obey our vector law of addition. Square root of P1 square plus P2 square plus 2 P1 P2 cos theta, and its direction will use a tan function. Tan alpha will be equal to P2 sin theta by P1 plus P2 cos theta. So if P1 is equal to P2, if P1 is equal to P2, let it be P, then P net will be equal to 2P cos theta by 2, and tan alpha, as they are same, we will get that will be equal to tan theta by 2. That implies alpha will be equal to theta by 2. So I'll give you one example based on this. Just look at this example. If you are given like this, there are two dipoles of, they gave like this, there is one charge minus 2q and another charge q is there. This is at a distance d, and another charge q is also placed at a distance d, and these two are inclined at an angle of 120 degrees. So out of this minus 2q, one charge will provide a dipole with a dipole moment P, that is Q into D. Of course, both the dipoles will have same dipole moment. So that net dipole moment you can write like this 2p cos theta by 2, or that will be 2p cos 120 by 2, or cos 60. Cos 60 is 1 by 2, so that it will be p. And if they ask it for a direction, alpha is equal to theta by 2, so that that will be equal to 120 by 2, which is 60 degrees. So this kind of questions we can expect based on this. Sometimes they will define coordinates also, very important. Now for this dipole, we'll find electric field due to this dipole at an axial point as well as equatorial point. Electric field due to a dipole. So that first case will be like this: at an axial point, at an axial point. If suppose we are having a dipole with this negative charge and positive charge, they are separated by a fixed distance 2L, and from the center of the dipole we are considering a point P along the axis which is at a distance R, so that this positive charge will be at a distance of, as total length is L, this will also be L and this will also be L. So if I'll assume that positive charge distance as R1 and negative charge distance as R2, R1 will be equal to R minus L and R2 will be equal to R plus L, and due to positive charge the field will be directed away. I'll write E1, and due to negative charge the field will be directed inward. I'll write E2. So net electric field we can write like this. It will be E will be equal to, as positive field is directed away and negative field is directed inwards, we have to write that as E1 minus E2. That will be, both the charges are having same magnitude, so that it will be KQ. I can take out common, 1 by R1 square minus 1 by R2 square, or this will be equal to KQ into 1 by R1 square, means it will be R minus L whole square, and R2 square means it will be R plus L whole square. So if we'll take LCM, we'll get KQ into R plus L whole square minus R minus L whole square by R square minus L square whole square. So here A plus B whole square minus A minus B whole square is there. So from this, KQ into, it will be 4AB 4RL by R square minus L square whole square. Or from this I can write the same equation, 2K into Q into 2L into R by R square minus L square whole square. And just now we defined dipole moment, so that electric field at an axial point, it will be equal to 2kpr by R square minus L square whole square, and we got this as a positive value, so that we can give one conclusion point like this: this field will be in the direction of, field is in the direction of dipole moment. Or else they may ask you one question like this: what is angle between axial field and dipole moment? Angle between axial field and dipole moment, that is 0 degrees, both are in the same direction. And here we'll have one point called short dipoles. If you are mentioned like this about short dipole, that means the position of the dipole from that particular point is very large, or else length of the dipole is very small, then in the denominator we can ignore this L. So axial field due to a short dipole will be equal to 2kp by r cube, and of course here k is nothing but 1 by 4 pi epsilon naught. So you can expect some questions based on this short dipole also. This is electric field about at an axial point due to a short dipole. Now that second case will be like this: electric field at an equatorial point, electric field at an equatorial point. So equatorial point means here it will be like this: if you are having a negative charge and positive charge, both are separated by a fixed distance from the center. If suppose there is a point is there at this particular point P, and as we know this is L, this will also be L, and if this distance is R, that particular point from both the charges, it will be at the same distance D, that will be equal to square root of R square plus L square, and due to positive charge field will be directed away, and due to negative charge field will be directed inwards, but both will have same magnitude. So magnitude of positive field as well as negative field will be same, and it is given as k q by d square, but directions wise they are different. If this angle is theta, in this direction we will have this is theta, this is also theta. So both the cos components gets added up to give that net field, and sine components gets cancelled, so that we'll have net electric field along y-axis 0, we'll have only net electric field along x-axis. That net electric field we can write like this: E will be equal to 2E cos theta with a minus sign because that is along negative x-axis. So minus 2 into kq by d square into cos theta, that cos theta is nothing but adjacent side by hypotenuse. So we can write like this: minus 2 k q by d square into adjacent side is how much? L, and hypotenuse side is d. So that it will be minus k q into 2L is nothing but dipole moment by d cube, or we can write like this: minus kp by r square plus L square whole power of 3 by 2. So here this is expression for equatorial field, and if it is a, they asked for what is its direction. Equatorial field is in a direction opposite to the dipole moment. This is dipole moment direction. Equatorial field is in a direction opposite to the dipole moment, or else they may ask you what is the angle between equatorial field and dipole moment. Angle between equatorial field and dipole moment is 180 degrees. That means they are anti-parallel. The same question we can extend like this: angle between equatorial field and axial field, it is 180 degrees. And this point also they will ask about short dipole. Short dipole means R will be very much greater than L. In that case, equatorial field will be equal to minus Kp by R cube. So this is about axial field and equatorial field due to a dipole. Now we'll discuss about the third case at any point in the plane due to a short dipole. Electric field due to a sharp dipole at any point in the plane. At any point in the plane. So if you are given like this, there is a short dipole like this. Its dipole moment is P and it is inclined at an angle. Whatever point we are considering, that point is inclined at an angle theta. Let this point be A. This dipole, we can resolve that into components. Along that line, it will be P cos theta, and perpendicular to that line, it will be P sin theta. And for P cos theta and P sin theta, that center is same. From the center, the distance is R only. But for P cos theta, that point A will be an axial point. So that we'll have one field like this. If I assume that as along x-axis, Ex will be equal to, it's an axial point, so that it will be 2 Kp cos theta by R cube. And for P sin theta, it is an equatorial point, so that let it be Ey, that Ey will be equal to Kp sin theta by R cube, and these two are mutually perpendicular, so that their resultant, if we need, we have to take that square root of x component square plus y component square. I can bring Kp by R cube outside, so that I left with square root of 4 cos square theta plus sin square theta, or that will be equal to Kp by R cube into square root of 3 cos square theta plus 1. This is magnitude of that field. And what is its direction if they ask? If I assume this angle as phi, and with the horizontal already this line is making an angle theta, so that if they ask it for direction, so that tan phi will be equal to Ey by Ex, that is Ey is Kp sin theta by R cube. So Kp by R cube, Kp by R cube gets cancelled. We left with half sin theta by cos theta, or that will be equal to half tan theta, or from this phi will be equal to tan inverse of half tan theta. So now they may ask you like this, with the dipole, what is that angle? If they ask, that will be definitely theta plus phi, because dipole is directed along positive x-axis. This kind of questions you can expect based on this electric dipole due to a short dipole at any point in the plane. Now, dipole placed in uniform electric field, dipole placed in uniform electric field. Suppose there is a region in which electric field is directed along positive x-axis, in which a dipole is placed at some angle. Dipole means will have a positive charge and negative charge. If this length is 2L, that is making an angle theta. So positive charge always experience a force in the direction of field. The field strength is E. That force will be QE in the direction of field. and this force will be QE in a direction opposite to the field. So net force acting on the dipole in a uniform electric field will be 0 because two equal forces acting in opposite direction, but they are not acting at same point, so that net torque is not equal to 0. We have to find that torque. For that, if this angle is theta, perpendicular distance between the two forces is 2L sine theta, then the torque will be equal to force acting at one point into that perpendicular distance, that will be equal to QE into 2L sine theta, or that will be equal to Q into 2L, that will be PE sine theta, or this torque we can express as P bar cross E bar. So we'll have some questions based on this, or else we'll have some questions based on this equation. And if theta is equal to 0, torque will be 0, or if theta is equal to 180 degrees, then also torque will be 0. But if theta is equal to 90 degrees, torque will be maximum. That maximum torque will be equal to PE, dipole moment into electric field. We'll have some questions based on this. And after this, as there is only torque, there is no external force, it will undergo pure rotational motion. It will move in a circular path about its center of mass, dipole. They will ask you what is time period of rotation of dipole. Time period of rotation of dipole. For that, as we are having torque is equal to PE sine theta, this torque we can write like this, I alpha. For small angle approximations, we can write PE into theta, or alpha will be equal to PE by I into theta. If we compare with our general equation omega square theta, this is from our simple harmonic motion chapter, we can get omega will be equal to square root of PE by I. So from this, time period of oscillation will be 2 pi by omega, or that will be equal to 2 pi into square root of I by PE. So this is about time period, and this is about angular velocity. So here you may get one doubt, how we'll get that moment of inertia. For that they will mention mass of both the charges. If center of mass is there here, this R1, R2 you can find. Suppose M1 is the mass of the negative charge and M2 is mass of the positive charge. That moment of inertia will be M1 R1 square plus M2 R2 square, where R1 will be equal to M2 by M1 plus M2 into distance between the two charges, and R2 will be equal to M1 by M1 plus M2 into distance between the two charges. Now, next we'll have one more interesting point. As it is rotating due to the torque acting by that actional field, work done by the torque, work done by the torque will be stored as potential energy. Work done by the torque will be stored as potential energy. For small angles, dW is equal to tau d theta. The tau is given as PE sine theta d theta. And if I need total work done, definitely I have to integrate. That work done will be equal to integration of dW, that will be equal to, I can bring that PE outside, integration of sine theta d theta, or from this what is integration of sine theta means, it will be PE with a minus sign, integration of sine theta is cos theta, so that this will be stored as potential energy and U will be equal to minus PE cos theta, or else this will be equal to minus P bar dot E bar. So these two equations are also very important for solving some numericals. We have some direct questions based on this. And if theta is 0, cos 0 is 1, so potential energy will be minimum, that is minus PE. We'll call this as stable equilibrium position. And if theta is equal to 90 degrees, cos 90 is 0, U will be 0, and theta is 180 degrees, cos 180 is minus 1. So potential energy will be maximum. That maximum potential energy will be plus PE, which is unstable equilibrium. So we'll have some questions based on this. And sometimes they'll give you two angular positions. For that, if suppose for that integration, if they gave limits, initially it is at an angular position of theta 1, finally it moved to an angular position theta 2, sin theta d theta will be there. So as integration of sin theta is minus PE cos theta within the limits theta 1 to theta 2, or this will be equal to PE into cos theta 1 minus cos theta 2. So you'll have some questions based on this also. If suppose initially at an angle of 30 degrees, after that it was rotated by an angle of 60 degrees, what is work done? We have to use this. For a given particular angular position, we have to use this. So this is about potential energy stored due to rotation of that dipole. Then we'll have one more interesting point like this: force between two dipoles, or this comes under the category of dipole placed in non-uniform field. If dipole is placed in non-uniform field, net torque is not equal to 0, and even net force is not equal to 0. In NEET level, they may not ask this much depth, but for JEE, you can expect some questions. For that, we are having two different cases: force between two short dipoles, force between two short dipoles when they placed along same line. Same line. That means if suppose they gave like this, two dipoles were there. One is having dipole moment P1 and the other one is having dipole moment P2. Their center to center distance is there along the same line, and their center to center distance is R. So definitely due to P1 there will be some electric field. For P1 it is an axial point, so that electric field is given as 2k P1 by R cube, and it is in the direction of P2. As both are in same direction, definitely potential energy of the system will be equal to minus P2 E1, because it is a stable equilibrium position. So that force will be equal to minus du by dr, that will be equal to minus 2k P1 P2, all are constants, d by dr of 1 by r cube. I can bring that outside. So now minus 2k P1 P2, as we are having this differentiation of 1 by r cube, minus 1 by r power of 4 into 3 will be there. So that this will be equal to minus 6k P1 P2 by r power of 4, because already one minus in u is there, we are having an additional minus, that's why this becomes plus. So finally we will get that force as minus 6k P1 P2 by r power of 4. So that this negative sign implies force is attractive. And you will have some questions like this. Force is inversely proportional to fourth power of distance between the two dipoles. This is about force between the two dipoles. Now the second case will be like this. If the two dipoles were parallel to each other, if the two dipoles were parallel to each other, that means that situation will be like this. If one dipole is like this and another dipole is also like this, so that this is dipole moment P1 and its dipole moment is P2, and center to center distance, let that be R, and due to this dipole P1, electric field will be in this direction, let that be E1. E1 will be equal to, as it is an equatorial point, it will be minus kp1, but I need not to write that as it is in opposite direction, kp1 by r cube. Potential energy will be positive, that will be p2 into e1, or that will be equal to kp1 p2 by r cube, as it is an unstable equilibrium, that's why we got positive value. So that now force will be like this, as F is equal to minus du by dr, or minus sign will be there, k p1 p2 differentiation of 1 by r cube, it will be minus of minus plus, we'll get that as minus 3k p1 p2 by r power of 4, and another minus sign will be there, so that it becomes plus. So and hence we'll get a positive value, means this force is always repulsive, and here also F is inversely proportional to R. So these are some models what you can expect based on electric dipole. They will ask you about dipole moment, net dipole moment, field due to a dipole at an axial point, equatorial point, and at any point in the space, and then they may ask you about torque, potential energy, and then force between two dipoles, the two cases just now I discussed. So that's it for this video. Have a great time. Please subscribe and share Progressive Physics Learning Profile. Have a great time.